You never know. So let's look at the problem statement here. In terms of the input information to address this fusion problem, so we are trying to fuse now the past distribution, and I'll define each of these, along with real-time information that comes to sensors, and then come up with the short-term future distribution. So every time that's the problem that we're trying to address when we say fusion. We look at the past distribution, we have real-time data coming in, and then we see what is the projected near-term future distribution. In this context, we have the historical travel time distribution, and we have the real-time travel time information. I haven't yet characterized how these look. I'll be doing so in a little bit. And so the information fusion, what it does is it outputs a short-term travel time distribution. So this is an example. Actually, it shows as though this is continuous, but the way we do it is we discretize it and address the problem. But this is essentially the problem that's being addressed. So as always, this is in a network context, and we have a network with n-links, arcs, and in terms of the information that we have, you'll see that on each link we have the historical travel time distribution. And the way we are looking at it is, on the current day, the historical travel time distribution is a constant distribution, so it's there. But then it can keep getting updated over time as we get information in time. So that's the starting point for us. The real-time travel time information that we obtain is coming not directly from the sensors themselves. So that's the starting point. We have the raw data. We project a travel time interval rather than a single value, because we collect that over some period of time, or we collect it over several vehicles for a particular time. And then the other element that I mentioned earlier, information quality, shows up in terms of two contexts. One is time delay, and I'll be defining that in just the next slide. And second one is the accuracy of the information that's being obtained. Both of these I'll be doing next. And the information quality varies among the various links. So the link travel time distribution is a discrete distribution. So the way we start out with this is we say that the actual travel time. So this is the actual travel time distribution. It consists of a set of states. So you have the states S1, S2, all the way up to Si. And then you have the probability associated with each state. So typically what that means is we break them down into small ranges, L1 lower bound of that, U1 upper bound, and so on. And these need not be of the same width either. So it really depends on the shape of that distribution. So this is so what that is saying is that the actual travel time on a link is a random variable. So in reality, that's what it is, because it changes with time. The second element is that this range has a lower bound and upper bound. I just mentioned that. The past link travel time distribution is the other piece of information that we use. The past link travel time distribution is looking at what we have on the current day up to the current time. So what is the distribution we have till that? So let's say that we have information just 5 minutes ago. Before, after that, we don't have any new information. We are talking about the distribution we have at that point. So anytime we have information, we update that to come up with the projected, short-term future link travel time distribution. So if every instance we have this information, we can update that past link travel time distribution to come up with this. So you'll see that in terms of the notation, you'll see H, or we call it historical, but actually it's the past one. This is the actual. And what you see, F here, is the fused. What we do here is we fuse the past information with the real-time information. And the objective is we want to get as close as possible to this. The next slide will actually show the real-time information in more detail. So that's why we do that. So we combine this with the real-time information to try to get this, which is what we call the short-term link travel time distribution. Now let's see what is the information we are going to combine with this. The real-time information I had mentioned has three elements. The information that we have in terms of the travel time, so it's R. Then we have the accuracy associated with that information. I'll be defining that as well. And delta T is what we call the time period. So the travel time interval, this is an interval with a lower bound and upper bound. The second one is the information accuracy. And what the information accuracy represents is it's a conditional probability that the real-time information range is present in the state in which the actual travel time is presented. So CA belongs to SIA means the actual travel time belongs to the state. So what is the conditional probability that the real-time travel time range also belongs to that state? So that's the probability that represents the information accuracy here. And the time delay is simply the difference in terms of the timestamps between when the data is collected and when the information is generated. And the further you go away from the time in which the data is generated, it's more likely that it's going to be less representative of the current conditions. So that's the other point to keep in mind. So the adaptive learning process, we look at the dynamic traffic network. There are flows which are dynamic here. We have real-time information from that through our sensors. At the same time, we have from this, we get the past travel time distribution that I talked about, so that's already there. This is where we use our information fusion model. So the parameters of the fusion are generated. So these x's are actually the weights, and we'll be talking about what these weights do. And then from that, we come up with the short-term travel time distribution. So we update t to t+1, and what that does is it changes the past distribution also to the next time step. And then this process keeps continuing. So this is the adaptive learning process that we have. Of course, the key point is, how do we come up with that? That's part of our information fusion model. So there's an optimization model that I'll be talking about in just a minute. So when we look at the past information versus real-time information on a link, the past information consists of these states. So you'll see that all of these states, the ones on the top, represent the past travel time information states here. So all that means is these are the states and there are probabilities associated with them. So all 6 of these will have the same upper diagram here. If it's the lower one, that's different. And so this is what is the past. H here means past. R means real-time information. So remember, the real-time information is provided as a range, the lower bound and upper bound. And there are 6 possibilities that exist. 3 of them belong to what is called the case where the historical or past travel time distribution covers the real-time information. See what happens here. All of the information, all of the range is within some of the states that already exist. Or you may have situations where part or full, or some of the elements of the real-time information range are outside the current set of states. So you see that here, here, and here, the whole amount is outside it. So these are the 6 possible cases. And so the question is, how do you fuse the two? So one of the things we need to do is first make it consistent before we can go to our information fusion problem. So the cases 2 and 3 can be combined or be converted to case 1, and I'll just show that. I don't know how to do it from there. Okay. So we start with one of those cases 2 or 3, all of which is within the current set of states. Then what we do is we simply divide those current states. So the states that are there here and here, we actually divide these into substates again, so that we now have a new set of states which now nicely have the range as part of it. And the reason for that is we want to cover the probabilities that we are going to actually consider as part of our computation. So this is the process by which we decompose it so that the cases 2 and 3 will nicely fall back to case 1, so that the range aligns itself with the current set of states there. Now for 4, 5, and 6, what happens is we can again, they are simple as well, because we simply associate new states with 0 probabilities there. So the way that's done, you can see the ones in the red, they'll have 0 probability, but then now you bring up 4 back to 1, 5 back to 2, and 6 back to 3. Okay? So, and once we do this, we are now at a point where this was already done. So we can go to our mathematical model. So in the mathematical model, what we are trying to do is minimize the uncertainty associated with the information. This the objective function is based on Shannon's entropy, and as you can see, this turns out to be a concave minimization problem. So you have here linear constraints, but you have an objective function. It is concave, and you try to minimize it. So it tends to be an NP-hard problem. So yeah.
Sure. In the previous slide, when you divide in state, what do you do with the probability? Don't you have to divide the probability
Yes, and they get, the way we do it is we do it in a, so we did based on the width of it. For now we just extrapolate or, based on that and proportionally. So if you want to call it proportional, exactly. So this is the minimizing the uncertainty of the travel time distribution. And I'll apologize, I won't have time to go into each notation. Instead, I'll try to go into the conceptual meaning of each of these and see what we're doing in this. So this is the objective function. The first set of constraints there, where it says basic data fusion model, this is the heart of the approach. The reason it's adaptive is what we're trying to solve for are these x's. Yeah, the x ones, the weights associated with the current, what we call the past distribution and the real-time information. So if the real-time information is good, then we want to weight higher. If it's not good, then we actually want to weight lower. And information accuracy helps us in doing that as well. So information quality actually helps us in doing that. In the past, there have been data fusion approaches which have used, fixed values for x, but not in this context. I'm saying more generally, they've used fixed values and then they just repeat the data fusion process, as an iterative process. Here, what we're trying to do is we're actually doing it based on, at each instant we want to actually update the short-term distribution. We do that. So the only reason we have this, for some of these we don't have the Q. I'll be explaining what the Q is. So the Q here is the posterior probability associated with the accuracy of the real-time information. I'll be actually showing what that is as well in just a little bit. And this is the probability, of course, we have seen that's the probability of the state in the past distribution. And based on that, we try to come up with the probability of the distribution that we're trying to determine. So I'll be showing some of these now. You'll see that there are convex combinations here, so there are constraints associated with that. Maybe the next one is where I need to show you.
So that's the probability of state I, right?
Yeah, this is the probability of state I.
So you could be using a different x for every different state?
Yes.
But then you have that constraint that makes sure that it's a distribution?
Yes, exactly. So that's what the convex, that constraint bottom again, you have the constraints that ensure that the probability identities are being addressed as well. So the information quality constraint, I'll just go to this to illustrate what this constraint does. It's easier to see it here. So for a link, the weight of the past information is proportional to the time delay. So if you have a long delay in terms of getting it, so your information, the information if you receive it currently, the real-time information, if you receive it for a long time, then you want to weigh the past information better because again, as with time delay, the information quality reduces. The second one is the weight of the, it's inversely proportional to accuracy of real-time information. The more accurate the information is, the more you want to weigh real-time information. Otherwise, you want to weigh the other one more. And the same thing goes with the variance of the travel time. If you have a higher variance for the travel time, then the weight associated with that distribution you want to reduce as well. So these are the three factors, and based on that, what we say is that these weights are standardized by assuming that for all links, these are these closed form expressions related to that. So in some ways, what we're trying to do is link it to time delay, we're trying to link it to information accuracy, and also the travel time variance as well. So, okay, so the next one is what is known as a consistency constraint. And I'll explain what this does as well. So the main objective of the consistency constraint, if you look at this short-term link travel time distribution, anytime we talk about short-term and so on, I mean, when you talk about distributions, distributions are based on multiple instances. They're not based on any one instance. And typically, when you have one long-term distribution where you collect data instances over multiple times and then base your probability distributions, then you're going to have robust ones. Now, when we actually have real-time information, okay? Now, it may be possible that that real-time information for one instance may actually be, going out of, it may be substantially different from what you currently have. Now, just because you have one instance